Intro: our planet appears as a serene oasis against a vast cosmic desert. But beneath this calm facade, a dynamic force invisible but powerful, constantly shaping our world in unseen ways. For millennia, mankind has looked to the stars to find their way, unaware that an invisible guide silently guided them. This guide, the Earth's magnetic field, an invisible shield, was our silent protector, shielding us from the merciless solar winds and cosmic radiations. But what if this constant of our lives was on the verge of a colossal change, a change so profound that it could alter the way we live our lives? Deep beneath our feet, in the heart of our planet, lies the key to this mystery, a restless ocean of molten iron churning and creating a magnetic force that envelops our world. That this force is not as constant as we once thought. Scientists have unearthed evidence, hidden in the very bowels of our planet, that tells the story of an ever-changing world, a world of flipping poles, changing the direction of the magnetic field and turning the world as we know it upside down. This is the story of Earth's geomagnetic inversions, a phenomenon as mysterious as it is fascinating. Our story begins with an invisible force that has imperceptibly changed the course of our planet's history. That force is the Earth's magnetic field, a complex and dynamic energy that extends far beyond the planet's surface into the space around us. Since ancient times, this magnetic field has been a silent guide for explorers and mariners, leading them through uncharted waters. It is a force so subtle that it goes unnoticed, yet so powerful that it has played an important part in the survival and development of civilizations. Deep inside the Earth is the heart of this magnetic force. Here, in the outer core, a bubbling ocean of molten iron generates the magnetic field. This motion, caused by the Earth's rotation, creates the dynamo effect, a process that maintains the magnetic field for billions of years. This field is not just a landmark for navigation, it is a shield. It reflects harmful solar winds and cosmic radiation, protecting our atmosphere and ensuring the survival of life on Earth. But this guardian is not as unchanging as it seems. Throughout Earth's history, the magnetic field has undergone dramatic transformations, geomagnetic inversions. These are periods when the magnetic poles change, with north becoming south and vice versa. Evidence of these changes is captured in the very stones of our planet. As volcanic lava cools and hardens, the minerals within align with the Earth's magnetic field at the time. By studying such rocks, scientists have discovered that our planet has undergone many changes. These changes do not happen suddenly. They occur over millennia. The field weakens, becomes chaotic, and gradually restores the opposite orientation. The reason for these changes remains one of the greatest mysteries of geoscience. As we delve deeper into this mystery, we begin to realize the immense power and fragility of this invisible shield. The history of the Earth's magnetic field is a story of constant change, a reminder of the dynamic nature of our planet. As we delve into the past evidence to unlock the mysteries of geomagnetic inversions, we turn to the Earth itself, our most reliable historian. The geologic record contains evidence of these monumental shifts. Volcanic rocks, especially basalt, have become invaluable in this kind of research. As we mentioned, as lava cools and hardens, the tiny magnetic minerals within it align with the Earth's magnetic field. This natural recording process creates a timeline of the Earth's magnetic history, locked within these ancient rocks. While studying these rocks, geologists discovered a startling fact. Over the last billion years, the Earth's magnetic field has reversed hundreds of times. The most recent of these reversals, the Brunnes-Matuyama reversal, occurred about 781,000 years ago. These reversals are irregular and unpredictable, with intervals ranging from tens of thousands to millions of years. This process is gradual and takes thousands of years. Another piece of evidence comes from the ocean floor. Here, magnetic striping bands of rock with alternating magnetic orientation coincides with mid-ocean ridges. As new rocks form and spread out from these ridges, they record the current orientation of the magnetic field, creating a symmetrical pattern of these reversals on either side of the ridge. Scientists have recently observed changes that hint at a potential upcoming reversal. Satellites and observatories have detected a gradual weakening of the magnetic field and increased movement of the North Magnetic Pole. The magnetic North Pole, once firmly established in the Canadian Arctic, is now drifting with acceleration towards Siberia. This movement, although not a definitive sign of an imminent reversal, is a clear indication of the dynamic nature of the magnetic field. Other indications include the development of the South Atlantic anomaly, an area where Earth's magnetic field is much weaker. This anomaly has grown and deepened over time, affecting satellites and spacecraft. As we piece together these clues from the past and present, the history of geomagnetic inversions becomes clearer. These historical and contemporary observations not only reveal the dynamic nature of our planet's magnetic field, but also remind us of the ever-changing nature of the world in which we live. Mechanics. To understand geomagnetic inversions, we must travel deep into the heart of the planet, to a place where intense heat and pressure produce one of the most mysterious phenomena on Earth. The core, located at the center of the Earth, is divided into two parts, a solid inner core and a liquid outer core. The outer core, consisting mainly of iron and nickel, is in constant motion due to Earth's rotation and thermal convection. The movement of liquid metal generates electric currents, which, in turn, create magnetic fields. This process, known as the geodynamo, is the driving force behind Earth's magnetic field. The dynamics of the outer core are complex and not fully understood. However, scientists believe that the Coriolis effect, a consequence of the Earth's rotation, plays a decisive role in the configuration of the magnetic field. The Coriolis effect causes convection currents in the outer core to spiral, creating swirling vortices. These vortices are thought to organize magnetic field lines, keeping the magnetic poles aligned. But what happens during a geomagnetic reversal? Current scientific understanding suggests that these reversals begin with a weakening of the magnetic field. This weakening can disrupt the alignment of the force lines, making them unstable and chaotic. As the field weakens, the influence of the Coriolis effect on the motion of the outer core decreases. This reduction in influence allows the magnetic field lines to realign in the opposite orientation, effectively reversing the poles. The invisible shield. Let's consider the Earth's magnetic field not only as a compass reference point, but also as a vital protector. The invisible shield, built deep inside the planet, is our first line of defense against harsh solar radiation and cosmic threats. The Sun, a fiery cauldron of nuclear reactions, constantly emits solar-wind streams of charged particles that can be devastating to life and technology. However, the Earth's magnetic field deflects these particles, creating a safe harbor for life to flourish. This magnetic shield also protects us from cosmic rays, high-energy particles from distant supernovae, and other cosmic events. Without such protection, these rays could pose a serious threat to humanity's biological systems and electronic infrastructure. However, during a geomagnetic field inversion, this protective shield is significantly weakened. This weakening can lead to an increase in radiation impact on the Earth's surface. The potential consequences of such increased radiation are profound. It can affect climatic conditions, potentially leading to dramatic changes in weather. Elevated radiation can also have biological consequences, affecting everything from human health to the behavior of animals, especially those that use magnetic fields to navigate. Moreover, a weakened magnetic field could leave our technology vulnerable. Satellites, power grids, and communication systems could be jeopardized by increased solar and cosmic radiation. Simulations show that the magnetic field is in turmoil, with multiple poles appearing and disappearing and magnetic lines of force moving and changing in a complex pattern. Global implications. What about the potential global implications of a geomagnetic reversal and humanity's preparedness for such an event? This phenomenon, although a natural part of the Earth's geological cycle, poses serious challenges in our technologically oriented world. On the one hand, geologists discuss the likelihood of such an event emphasizing its inevitability given Earth's history. On the other hand, scientists express concern about the vulnerability of our satellite networks, power grids, and communication systems. A weakened magnetic field could lead to increased solar radiation, potentially disrupting such critical technologies. Also, let's not forget about possible climate change. Although the exact effects are unknown, some models suggest that shifts in the magnetic field could affect weather patterns, potentially leading to extreme and unpredictable weather. One thing is certain: the impact on wildlife, especially migratory species like birds and marine animals that use magnetic fields for navigation, could be catastrophic. Disturbances could lead to ecological imbalances and affect biodiversity. Research aimed at understanding and predicting the timing and consequences of geomagnetic reversals is ongoing. The need for global cooperation in such research is key to developing strategies to mitigate potential risks. It is a reminder that, while we may not be able to prevent natural events of this magnitude, through understanding and preparation, we can mitigate their impacts. The future. As we continue our journey, we turn our attention to the future, specifically how scientists are tracking and predicting changes in the Earth's magnetic field. At the forefront of this research is a fleet of sophisticated satellites, equipped with instruments capable of measuring all the subtleties of the magnetic field with unprecedented precision. Projects such as the European Space Agency's SWARM mission provide valuable data on magnetic field strength, direction, and anomalies. These satellites are complemented by a network of ground-based observatories that continuously monitor the magnetic field at various points on the Earth's surface. Together, these instruments offer a comprehensive view of the behavior of the magnetic field and its variations over time. The data collected are not just for scientific curiosity, they play a crucial role in predicting the future of the Earth's magnetic field. By understanding the patterns and causes of past geomagnetic reversals, scientists hope to better predict when the next reversal might occur. While the exact consequences of a future reversal are still a matter of research and debate, the consensus is clear: understanding and preparing for such an event is crucial. This involves not only scientific research, but also public awareness and international cooperation. Just as we've overcome the challenges of our past, we are ready to face the future with knowledge, technology, and a spirit of cooperation. The study of the Earth's magnetic field, from its historical changes to cutting-edge research aimed at understanding its future, emphasizes the interconnectedness of science, technology, and society. It's a reminder of our place in the vast cosmos and the ongoing need to understand and respect the forces that shape our world.